Okay, so up to this point, I talked about the important concept related to parallel computing, from the design strategy to the hardware architecture. The next part of today's lecture, I will talk about heterogeneous computing. Now, I listed two papers on the slide and also on a blackboard. These two papers are important papers that were published in the past decade. And the reason I chose these two papers is that one is talking about from the chip design or processor design perspective, what has been the trend to go from a single processor core to multiple cores. And when we have multiple cores, how we need to efficiently utilize the on-chip transistors to gain more performance. The second paper is a survey paper published 4 years later than that one. And this paper talks a little bit more about how computer architects, programmers, and researchers are moving away from the debate of CPU versus GPU, which one is better, towards a more cooperative thinking. When we have CPU and GPU, how we should use them in the best way to maximize both performance, or maximize the utilization of both. So the conversation has shifted from debating which one is better to how we can use them together. And that's in fact the goal of this course, to show you, okay, now we have these heterogeneous processors, how we can use them better to achieve our goal, to address our problems, to meet the application requirement. So I'm going to go over some of the main points in the first paper and briefly about the second paper. But I will encourage you to read these two papers after class. So the big picture about what happened in the past 20 years, now close to 30 years, the microprocessor's performance has gained several order of magnitude increase, primarily driven by transistor speed, energy scaling, and microarchitecture advances. And also, during the past 2 years, people in the microprocessor industry have been facing new challenges in shrinking transistor size and also the energy limit. So these point to a trend that goes from a single core performance towards multi-core performance, or throughput-wise performance. And also, it points to the direction of large-scale parallelism using heterogeneous cores, and also use accelerators. This is a picture that shows some processors from Intel, although these are all very old processors. But this picture gives you an idea how many transistors are there on a single chip, from 1971 to 2009, so about 10 years ago. You can see that the transistor counts increased dramatically. Also, the chip size increases, which translates to more transistors and count, and also the speed of these transistors. The performance of these transistors increased by nearly 5 orders of magnitude. One person named Robert Dinard, he has a recipe to kind of give you a rough estimation about the dimension changes of the transistors. So it says, transistor dimensions about reduction about 30% every generation. Also, we have the famous law about how the transistors doubles every 18 months. transistor size counts. The major benefit of transistor scaling is that it allows you to have more transistors on a single chip. And these transistors can be used for different purposes. Could be logic, could be memory, and people try different ways to better utilize them. Also, the transistor performance increases by 40% so in terms of the frequency and delay, frequency increase and delay reduction. Supply voltage reduce, which reduce energy subsequently, and that's a big deal. What we show in this diagram is, on the other hand, try to give you a sense about how these architecture designs within processors improve the performance and what are the trends. So what we see here on the x-axis is some tricks that people have been using to put new things or new design into microprocessors, and we're talking about CPUs. First one on the left is on-die cache pipeline. On-die cache is the small fast memory that you put on chip to take advantage of the locality of these programs. Also, pipeline design is to make sure it supports the frequency scaling. The second on the x-axis is the superscalar. Superscalar is where you have multiple instructions can be issued, executed at the same time. And later on, you have this out-of-order speculative execution, where you can actually execute future instruction ahead of time, just pretend there's no impact to them, or pretend that they will be executed. The reality is there are chances, for example, if there's a branch instruction, the future instruction should not be executed. So that's why it's called speculative. So it's a guess. But people have been designing ways to make this guess in the hope that to gain some on the performance. Deep pipeline is try to have a large number of stages in the pipeline to even scale the operation frequency, and eventually people are branching to different ways back to non-deep pipeline, and instead adding more cores onto the chip. And these colored bars are kind of showing you what's the area, chip area, and performance on integer operation, floating point operation, and energy efficiency. So what we see really is for these different techniques, the increase compared to the previous generation, the increase on the performance is actually diminishing. So you don't see big increase every year after generation due to these different designs. And that's not so good news, which means that if you try all the smart things, tricks that you put into these processors, you cannot just push these performance any further, as you expected, as you hope. On the other hand, one thing is good news. That's the energy efficiency. Energy efficiency is now here measured as integer performance over watts, and that increased by, close to four times. That's important because if you cannot push the performance further, then let's try to pack more cores onto the die, onto the chip. And because your energy efficiency increase, you can afford to do that. So that gives a chance to, have the processor do more in terms of throughput. So you have more tasks can be done compared to the previous generations. But for a single task, it may not be faster than before. But in terms of number of tasks it can perform, that's the throughput, and that improved. There's another rule. We'll actually use this down in the later slides. It's called a Pollack's rule. It's very simple. What this person observes by plotting this. On the x-axis is the area, and y-axis is the performance. You don't have to care too much about the absolute value, but what it shows here is that the performance increase as the square root of the number of transistors or area of a processor. So as the area increase, performance increase relatively, and the relation is about the square root of the number of transistors. And this diagram is, x and y-axis both are in exponential scale, log scale. DRAM, on the other hand, it also improves, but the improvement is much slower compared to processors, and the density increase nearly doubles every 2 years, but the performance in terms of read-write speed is not keeping up. Why? Because DRAMs are optimized for density and low cost, and also because of internal design, it's hard to push the speed further. As a result, people are relying more and more on-die caches. These are old diagrams, and now we have 7 nanometers, 4 nanometer technology, but the trend is the same. You see more and more on-chip caches, and now for a Xeon processor, easily we can have 24 megabytes of cache or even more on a processor chip. Also, this shows the transistor performance increase and integer performance increase. What is the trend, which was helpful? The observation is that the transistor scaling benefits reduced. We don't gain much. Even we shrink the transistors size and increase the number of transistors. The total energy budget is flat. This is primarily due to the packaging requirement and also the pervasive mobile and embedded computing applications. The transistor density and count increases, and the need for increasing locality and reduced bandwidth per operation, because you cannot afford to go off chip. If you go off chip, you hit the DRAM and your performance gain just suddenly lost. And from power consumption perspective, leakage power becomes predominant because transistor is not a perfect switch, so there's always a leaking current when you switch on and off the transistors. As you decrease the supply voltage, and this becomes more dominant as a part of the total power consumption. Same thing about the supply voltage. You cannot scale down even further because the physics limitation. So you cannot just reduce supply voltage to reduce the energy and power consumption. I'll skip some of these. Okay, so people always have big goals. The overarching goal is that we want to be able to achieve terabit or even more operation. But just relying on the frequency increase, the reduction in supply voltage, reduction on the capacitance of these connections and wires, you cannot go very far. The transistor count can be increased by several times, but due to the Pollak's rule, let's do a simple calculation. If you have a single core with 150 million transistors, compared to 25 million transistor core, you have about 6 times of transistors. Pollak's rule is that your performance gain is about the square root of the number of transistors gain. So if you have 6 times of transistors, you're talking about square root of 6, so about 2.5 times performance gain. And that's far from the 20, 30, even 100,000 times of gain that we were expecting. So we cannot do that. On the other hand, let's say you have 150 million transistors. How are you going to use it? Does it make sense to have 80 megabyte of cache on the core? It's debatable, but the question is how you have to design your cores to saturate these 8 megabytes of cache. What kind of workload you have to run on these kind of cores? So in this paper, there's some discussions how we should utilize these transistors. How we should, for example, utilize the transistors to make processor cores. So it's the the title here, organizing the logic. How do we design multiple cores and customize them? How are we gonna organize the cores? Let's say we use that example. We can have a 25 million transistor core versus a 150 million transistor core, but the performance gain is only about 6 times, even though you have 2.5 times, even though you have 6 times of transistors. The way to better utilize these cores, if you want to dedicate them to logic, to computing logic, we should think about customized hardware in terms of fixed function accelerators, programmable accelerators, and even maybe put an FPGA type of logic together with the cores. This is a good example to explain the idea why it may not be beneficial to have large cores, uniformly large cores. Let's say we have this 150 million transistors. Okay, each core in this first design we have 25 million transistors. So in theory, you can have 6 of these cores on this chip. So what we have here is, let's say for these large cores, okay, each one of them same size, the throughput in terms of performance, we measure in throughput. Throughput is 1. Okay, and here we don't have the small cores that we will see in the next 2 designs. So the total throughput is going to be 1 times 6. You would say that, it's not too bad. Let's say if we design the chip differently, instead of having 6 cores, each takes 25 million transistors, let's make smaller cores, simpler cores, which could be running fewer instructions at a time. But each core takes 5 million transistors. So compared to the 6 cores, now we suddenly have 30 cores, given total 150 million transistors. Okay, it's a simple math here. Now, using Pollock's rule, if that holds, then we're talking about worse performance than the bigger cores. How worse? So we're going to have 5 divided by 25. That's the number of transistors of the large core, and we take the square root of that value. So we're talking about 0.45 as the throughput compared to this unit throughput of the large cores. But we can do many things at the same time by using these 30 small cores. So 30 times this 0.45, we actually have a very appealing number, 13. This 13 doesn't mean that the smaller cores are going to each is better than the big core. It's not. But overall, in terms of throughput, these 30 cores are better than 6 big cores. And you can do a trade-off, because in some cases you not only require the throughput, in some cases you require the single thread performance or single core performance. So let's keep a few big cores. So what we see here on the third design is that we have 2 large cores, each is 25 million transistors, and for the rest of the transistors, we use them to build small cores, 5 million transistors each. So you can do the calculation. Now the total throughput is going to be 11. Of course, worse than all the large number of smaller cores, But the trade-off is that we now have a chance, if needed, we can use these large cores to run these bigger tasks. So this is a very nice example to show you that it may not be beneficial to have large cores. In some cases, small cores is better in terms of throughput. And we can also have this design option to have a mix of these to balance the need. So we can have these big cores, smaller cores, and those are kind of general purpose CPU cores. Another way to utilize these logic is to use them to build customized hardware. We can use these logics to build specific function units, multipliers, or FFT unit, and we can use some logic to perform wiring and interconnect for moving the data around. And we can reduce instruction sequence overhead at some cost of generality, because these hardware accelerators, they could be fixed function. In that case, you cannot use them to do something else. But you can design them in a very efficient way. You can achieve very high energy efficiency than the general purpose designs. As a result, nowadays you see many of these so-called system on chip, and many embedded processors are of this kind. So they have some computing cores in a chip. Also, they have different DSP unit, some sort of controllers for display, for USB drives, and also on chip they have different interconnects to connect these cores or DSPs to other peripherals. I'll skip some of these. This paper talks about the logic organization, discuss these different challenges, and it discuss about this 90 and 10 split versus 10 by 10 split. What this means is that in a traditional design principle, people try to use 90% of the transistors for building sophisticated superscalar out-of-order processors to achieve very good single-thread performance. As we see earlier, that this may not be beneficial. So instead of having this 90% versus 10%, people have been thinking about, okay, can we do 10%? And each of these 10% can be devoted into cores or customized hardware unit, dedicated accelerators, etc. So there are different possibilities. Data movement is another important concept, and it's crucial for any parallel computing paradigms, hardware, because if you have dependencies, you have to move data around. You can move data up, down, memory hierarchy. In that case, you need very efficient memory hierarchy, and that's why we see, from the processor you have caches. You have first level cache, second level cache, even third level cache. And when you go off chip, you have different memory components, DRAM, and for DRAM you can have different speed of DRAM, and then later on you can have lower level storage systems. If you don't go up down in the memory hierarchy, then among the processors you have to have ways to transfer data back and forth, and that's where we have this network on chip. Network on chip is interconnects that's built onto microprocessor die. It based on packet switching. It's very energy intensive. So the whole suite of research on building these network on chip designs to reduce the energy consumption. But it's important when you have multiple cores, you have to have this for them to communicate be able to send important data quickly to each other. So the paper discussed about the challenges in the data movement, also the energy efficiency perspective. For the energy, one typical design is to do voltage scaling. So not only you can have mixtures of big cores and small cores, you can also run these cores at different speed. So F stands for the frequency, so you can design different clock signals to drive these cores at different speed. And that will greatly reduce the energy efficiency because you can tune these operations based on your workload, based on how you schedule the tasks. Software challenge is an important thing. We will see more and more throughout this course that to be able to design software, by software we kind of broadly speaking the CPU software, GPU software, or the FPGA design piece, although it's technically not software. But either way, the design framework, the programming language, these are all important for efficiently utilize the parallel resources in hardware. Let's see, software challenges. So this paper kind of lay out outline some basic design trends that have been observed in the past 20 plus years. So the performance of processor has increased dramatically, but at the same time face a lot of challenges due to transistor scaling, the physics limitations, and energy consumption. So the future microprocessors will be large large-scale parallelism, heterogeneous cores, maybe very few large cores with many smaller cores with flexible frequency and voltage. Also, there's an increasing trend to have different kinds of hardware accelerators built onto the chip, which leads to system-on-chip designs. And important consideration has been taken how to efficiently partition your data so that you don't have to move data around. Now, quickly, I want to say a few words about the second paper, the survey paper about CPU+GPU heterogeneous computing. We mentioned earlier that people have been talking about how we leverage these different processors in the same framework rather than choosing one of them, because each processor architecture has its own advantage. The evolution of hardware architecture, as we also saw from the previous paper, has gone through the increasing transistor count, increasing number of cores, increasing cache size, and also new technologies such as 3D stacking. 3D stacking is a way to better utilize the transistors, drastically increase the bandwidth of the memory. Also, the interconnects improves a lot. Off-chip wise, you have different high-speed interconnects, PCIe 3 and Thunderbolt NVLink. Those are all new interconnection technologies. Some are from single vendor, some are kind of industry standard. All these lead to acknowledging the strengths of different CPUs, which have different unique architecture strengths. And also, people have been thinking about how to match these algorithms requirement to future features of PUs. So this PU processor unit, or processing element, sometimes we say, it broadly refers to CPUs and GPUs and FPGAs. For the goal of improving the resource utilization, it tries to take advantage of the advances in the CPU design. To use this CPU/GPU heterogeneous architecture, or in our case, CPU-FPGA heterogeneous architecture, we need to talk about the algorithm level, program execution level partition techniques. There are different type of scheduling techniques when we run these workloads. Scheduling is concerned about when a subtask is decided to run on a particular processor. Also, we need to talk about workload partition, and this is concerned about data partition and task partition. So, we'll try to think about why a particular task is scheduled on a processor. So one problem we need to think about is when. The other problem we think about is how or why we need to have this particular task partitioned this way, and which processor we should put it on. There are many different kinds of programming languages and frameworks, OpenCL, CUDA, and then OpenMP, pthread, MKL, TBB. Now the last group, OpenMP, pthread, MKL, TBB, they are more on the CPU domain, whereas OpenCL and CUDA are on the other hand on different processors. In particular, OpenCL is generic to CPU, GPU, FPGA, and CUDA is specific to NVIDIA